Do you know why reg and where of Verilog create conceptual headache for each digital designer? Do you know how logic can replace both reg and where in either sequential or combinational logic design? Do you know how the extra bulge of x and z state is trimmed down in the bit construct? We will do a code comparison to fact check the difference of logic bit versus reg where side by side. So stay tuned, stay focused. Hey guys, welcome back. In today's episode, we'll discuss why bits and logic introduced over reg and where. In digital design, we use special languages to describe how circuits should behave. For many years, Verilog was the go-to language and it used keywords like reg and where to represent signals. But as technology advanced and designs became more complex, engineers needed a language that was more precise and less confusing. That's where SystemVerilog came in. One of the important improvements in SystemVerilog is the introduction of bit and logic as new types to replace reg and where in many situations. These new types are easier to understand, reduce mistakes in code, and help both simulators and synthesizers work better. In this presentation, we are going to explore why bit and logic were introduced, how they work compared to older types, and how they make digital design simpler, more powerful, and more reliable. So without any further delay, let's begin today's episode. So here is the menu for today. In this episode, we'll discuss the points: ambiguity in reg and where, that was in Verilog; simplified syntax with logic, that has the new entry in SystemVerilog; bit for two-state logic, and this is also a new entry in SystemVerilog. We'll talk about the two new things: backward compatibility, that is logic and bit will have backward compatibility, and we'll have a code comparison between Verilog and SystemVerilog, which comprises the reg where versus logic and bit. Finally, we will compare the reg and where with logic and bit, and that's how the episode will end. Now we'll move on to the next slide to begin our episode. Ambiguity in reg and where. In Verilog, the two main types of signals were reg and where, but over times, designer realized that these had some limitation and confusion. For example, reg sounds like it should always be a hardware register, but it's really just a variable for procedural assignments. And where always works with continuous assignments while limits its flexibility. These ambiguities made Verilog harder to work with, especially for larger or more complex designs. SystemVerilog addresses these issues by introducing logic and bit, offering clear, more consistent types that simplify coding and reduce errors. Now let us go with the slide. In Verilog, the use of reg and where had some limitation and ambiguities, which SystemVerilog aimed to address by introducing logic and bit. The new types improve clarity, simplify syntax, and reduce errors in the hardware design. Now we'll talk about the ambiguity in reg and where. Reg, the mission mark. Despite its name, reg does not, I emphasize does not, always represent a hardware register. It is simply a variable type that can hold value, is used in procedural blocks. So here you can see how the confusion is getting created. Where restriction. Where is only used for combinational logic and requires continuous assignments, that is the assign statement, making it less versatile. So now the namings are not according to the dictionary meaning. That is what we see here. Example in Verilog. Let us take a very small code. Here we have definition with where, we have a assign statement where C is A and B, only continuous assignment is valid for where, okay, and we have reg D, and here we have a always block with a passage of clock as a trigger, and here D receives the C through a sequential assignment, and this is valid for reg. So here you can see how the things are pretty much confusing and we have to maintain some decorum to use them. That was in Verilog. To sum up, range and where served their purpose in Verilog, but their limitations often led to confusion. Range didn't always mean a register and where could not be used in procedural blocks, which meant you had to constantly switch between the two. SystemVerilog improves on this by giving us logic and bit, which unify and simplify how we describe signals. They eliminate old ambiguity, support both combinational and sequential logic more intuitively, and help make your hardware design code cleaner and more robust. So we are done here with this particular slide and the example to show you. We'll move on to the next slide. Simplified syntax with logic. Now, we have seen the issues with range and where. Let's look at how the SystemVerilog simplify things using logic type. One of the best features of logic is that it can be used in both combinational and sequential logic. That means you no longer have to choose between range and where. Logic works in both cases without causing confusion or errors. This makes your code cleaner and easier to understand, especially when your designs grow larger, like in VLSI design. Simplified syntax with logic. Logic can replace both range and where, as it supports usage both combinational and sequential logic without any ambiguity. The distinction between where and range no longer necessary. I emphasize no longer necessary. Simplify the coding process. Logic does that. Example in SystemVerilog. So here goes a small example to demonstrate the logic. We define logic here, the keyword and the variables are here. We use the assign statement here and we use the always ff, and with the trigger is passage of clock. Here D receives C, it is the sequential logic. And here you can compare with the previous code which was very much similar, but we are jumbled up with range and where. Here we are very straightforward and we are using both the assign statement as well as this non-blocking assignment symbol here with the same logic. Earlier we used to get confused and sometimes mistake could be there with the Verilog code. Now logic gives you a free hand to code with both combinational and sequential logics as well as the continuous assignment as well as the non-blocking assignment. So you are free on your mind. With logic, SystemVerilog removes one of the Verilog's biggest pain points, having to constantly decide between range and where. You can use logic in procedural blocks for combinational assignments or even in always ff blocks, and all without worrying about mismatched usage. It simplifies the syntax, reduces the chance of making mistakes, and let your focus more on design logic rather than coding rules. So your head is less bugged while you are doing the coding. And that's all with this slide. Let's move on to the next slide. Bit for two-state logic. With the move to logic, SystemVerilog also brings stronger type checking. This means it helps catch more errors during the compilation, like mixing up range and where by mistake, which was easy doing in Verilog, but using logic, you can avoid the whole "is this procedural or continuous" question altogether. Along with that, SystemVerilog also introduced a bit type, a lightweight two-state data type that holds values 0 and 1. This is specifically useful for modeling simple elements like counters or registers, while unknown or high impedance states are not needed. Using bit makes simulation faster and uses less memory, which can really matter in larger designs. Stronger type checking. SystemVerilog enforces strict rules on logic, helping prevent errors like accidentally mixing range and where. Using logic in place of where or range eliminates errors caused by forgetting whether a signal is procedural or continuously assigned. Now we come to our topic of this slide, that is introduction of bit for two-state logic. Bit is a two-state data type that is 0 and 1. These two can be there only. Introduced to improve simulation performance and reduce memory usage. It avoids the worry of 4-state logic, right? Like 0, 1, in addition you get X and Z used by range and logic. So the bit gives you more flexibility with either 0 or 1. So you are much more now flexible. The cases where X and Z are not present and will not be present at any cost, you can go ahead with bit. It is ideal for modeling simple digital systems where X and Z are not required, that is registers and counters. We have an example here. We have a bit defined 3 down to 0 counter. It is 2-state efficient for counters. We have a always FF and we have a trigger of pausage of clock, and here counter receives counter plus 1, this non-blocking assignment. This simulation avoid 4-state overhead. That means now these 2 states are considered here and X and Z are excluded. So these additions, SystemVerilog not only clears up confusion, it actively helps prevent bugs before they happen. Logic simplifies your design by making sure signals are used correctly no matter where they appear and when you need performance and simplicity. Bit steps in as an efficient alternative for clean 2-state logic. Together, these improvements give you better tools for writing reliable, efficient, and more readable hardware code, all while reducing the simulation time and catching errors earlier in the process. So we're done with this slide. We'll move on to the next slide. Backward compatibility. One of the great things about SystemVerilog is that it doesn't break the compatibility with existing Verilog design. The new logic type is fully compatible with Rage and can be used in most cases where Rage or where would normally go. So you are transitioning from Verilog, you don't have to rewrite everything. That means you don't have to write every line of code again. However, for situations where you need a tri-state drivers or resolve signals, things logic can handle where is still available. This ensures SystemVerilog strikes a balance between modernizing the language and maintaining the flexibility with older designs. Here, the retained backward compatibility. Logic fully backward compatible with Rage can be used in most situations where Rage or where was used. Where still exist for cases where tri-state drivers or resolved signals are required, as logic cannot be used in such cases. Now key takeaways are: logic simplifies coding by replacing the rage and where without any ambiguity. That means with very swift move you can replace rage and where with logic. Bit improves the performance and it's ideal for 2-state systems. Bit actually drops the overhead of X and Z and that's how it becomes lightweight. To summarize, logic makes your code cleaner and more intuitive by replacing rage and where without the ambiguity. It is a direct upgrade that simplifies your work. Meanwhile, the bit type boosts the simulation performance and is ideal for systems that only need 2 states, that is 0 and 1. SystemVerilog offers these improvements while keeping the backward compatibility. This means you can take the advantage of the new features gradually without need for a full redesign. Now we are done with this particular slide, so let's move on. Code comparison example. Now in this slide we will compare 2 different codes, here and here. Here there will be a Verilog code and here there will be a SystemVerilog code, and we will compare line by line. So here goes the Verilog code using the rage and where, and here goes the SystemVerilog code using logic. Here we define the counter. You can compare, right? Here we have rage simply replaced with logic, and we have input like here we have used the logic, right? Simply we are using logic. That means we are simplifying the definition of the module. Here we have where enable and we have logic enable. So we have a enable and here we are using where, instead in the SystemVerilog we are using logic. We have assign statement. Okay, this remains same here and here. Next we have the always block here and always block here. You can see it is a old always block in Verilog and it is a always FF. Here we have the same trigger in both, and we have a reset condition here. Here in both cases we have a non-blocking assignment, right, for the count, and for enable, right, we have a non-blocking assignment same in both, and we have the end module same in both. So if you have a quick and closed loop, the logic has simplified between choosing the rage and where. It's very simple. On the left we have a typical Verilog code example that uses rage and where. As you can see, the count signal is defined as rage and enable as where, which requires a continuous assignment. The always block checks for this clock edges and resets the counter. On the right, see the equivalent of SystemVerilog code. Here the rage and where are replaced with the logic, which can be used in both combinational and sequential logic. The always block is also replaced with a always FF, which is specifically designed for sequential logic. This change makes the code thinner and easier to understand and easier to code also. To sum up, both code examples do the same thing. They implement a simple counter that increments at each clock cycle with a reset condition. However, the SystemVerilog version is more streamlined and modern. By replacing rage and where with logic, we simplify the code and remove any ambiguity. The use of always FF further clarifies that we are dealing with sequential logic. This example shows how SystemVerilog allows us to write more efficient, readable, and error-free hardware description while maintaining the same functionality as traditional Verilog. So you have a side-by-side comparison here, and we are done with this slide. So let's move on to the next slide. Comparison of rage and where versus logic and bit. So here we'll do the comparison by a table. In this slide, we will compare the older Verilog types rage and where with the newer SystemVerilog types logic and bit. While the rage and where have served their purpose in Verilog, they come with certain limitation and ambiguities as a burden that can lead to errors, especially as designs grow more complex. SystemVerilog introduces logic as a more flexible, unified type that can replace both rage and where, simplifying the design process, and bit, a new two-state type, is optimized for performance in systems where only values 0 and 1 are needed and x and z are not needed, reducing memory usage and simulation overhead. Now comes the comparison table. Rage and where, in point of versatility, requires distinction, and this is unified. So this distinction is a overhead to your brain as a coder, and here this overhead is gone. Your mind is relaxed. You are more flexible in coding. Type checking, this is weaker and this is stronger, so to prevent errors. This is internally done, right? State representation. We have 4 states, that means 1, 0 and x and z. Here we have a proper partitioning, right? Logic has 4 states and bit has 2 states. Use as you need. Performance, more overhead, not only to the code but also to your brain. Bit has a faster for simulation, and logic has a less overhead for your brain, and for performance we are using bit. Tri-state support, this requires where, and this requires where and logic. This requires where logic is not supported. So tri-state logic, we should stick to the old where. Okay, so that was the comparison chart, and it is very simple. Rage and where are still used in many legacy Verilog designs, but they can be confusing and lead to mistakes. SystemVerilog's logic and bit streamline the process, offering a more intuitive and efficient way to work with signals. Logic moves the ambiguity between rage and where, while bit provides an efficient alternative for simple two-state logic systems. So we are done with this particular slide, so let's move on. Thank you very much for watching up to this point, and don't forget to like, share and subscribe. In case you have some dislikes, put that as in words in the comment section down below. And bye for today.